All right, so we're going to do a session on gas, condensate, PVT, and in particular looking at depletion recovery performance. Okay. And one of the things that we're going to do is that we're going to try to show the consistency that you should expect and get when you compare equation of state calculations with a PVT program, simulating a constant volume depletion test, and a reservoir simulator simulating just depletion. That consistency of recovery factor, in particular for the condensate or the oil, is basically the goal. So we're looking at an EOS-based PVT model. So that we need. So we'll have to pick one out. And then we'll have to have a particular surface process that's important to define consistently. So this needs to be defined consistently. Between the basically the PVT simulator which we're going to use phase comp, and the reservoir simulator. Which we'll be using sensor. And okay. Let's see here. Because this here needs to be up here as well. In other words, we need to have the EOS-based PVT model defined consistently between the PVT simulator and the reservoir simulator. So we have the same EOS model in both simulators, and we have the same surface process in both simulators. And if you do that for a gas condensate, so if this is done properly, then you should get the following and very important consistency between the PVT simulator and the reservoir simulator. Okay, is that first you should get the same initial gas-oil ratio. We're going to talk mainly about oil-gas ratios, which is just the inverse of that. Okay, in the two models. With the same initial oil-gas ratio, you basically get the same oil in place, the same gas in place, if you will, for the two simulators. More important than that is that you should get the same, and when I say same, it's almost should be line thickness. Okay? Line thickness is almost the same. Because the same to a politician and the same to an engineer is different, right? Okay. The same oil recovery factor as a function of depletion pressure. The same recovery factor of both oil, which I'll write like that, surface oil, as a function of pressure, and it's easier, but surface gas as a function of pressure. For a depletion, and for the man, this is something is not right or good about the not sure what's causing this to go so slow. So it's going to be using a CVD test for the PVT simulator. And just depletion, blowdown, whatever you want to call it, depletion for the reservoir simulator. And here we're using phase comp, but that could be PVTI or PVT-SIM, whatever you like to use. And we're going to use sensor. Now that could be Eclipse 300 or GEM or whatever you want to use there. Okay. So this is our goal, and I'll just sketch the graphical. What we're going to be trying to create here is this is going to be our recovery factor, which is defined as the oil produced or condensate produced over the initial oil in place, or the cumulative gas. That's processed surface gas, not wet gas or well stream, but it's actually sales gas divided by the initial amount of sales gas in place. And that's a recovery factor from 0 to 100%. And then we're going to have pressure. We're going to have the initial reservoir pressure. We're going to have a dew point pressure. I'll just make a line like that. And then we'll have the gas recovery factor will look something like this. Okay, and that's gas. And the oil recovery factor will look how? What will that look like? Should we pick on Hamid, our guest, or not? You took courses in Calgary?
No.
You took some courses in Calgary?
Yes, I do.
Okay. Did you take any courses in gas condensate related?
No.
Then we don't pick on him. Okay. So how should the oil recovery look? Above the dew point.
There is no oil recovery above dew point.
I hope so. That's where we're making most of our money.
Maybe the oil from the wet gas.
The oil from the gas in solution. And you have the maximum amount of oil in solution in the gas above the dew point. So we're definitely making money in recovery of condensate. But what should it look like?
It should be constant.
The recovery should be constant? You mean it should look like this?
It should be linear.
No. Okay, let's just look at this. We have a hydrocarbon pore volume that everybody's okay with, right? So basically, if we take, well, that's our reservoir. Put some faults in there. If we take the initial fluid to the surface through some, let's say, just a simple two-stage separation. Okay. Get the gas off the stock tank. Okay. Now this here is what I'm going to call our surface process. That's the way I draw it. P, capital P with 2 lines under it. It's any process you like. We're gonna use a 2-stage, or we maybe use a more complicated, and we end up with, if we take all of the contents of this hydrocarbon pore volume, okay, to the surface at once, that's what the reservoir simulator will do, to tell you how much sales gas is there. This is our sales gas. Okay, and we play God. We just take everything from the reservoir through this process to the surface. And that gives us what? It gives us the initial gas in place. And then we get the surface oil. And that is what we call the initial oil in place. Condensate in place. I call it just oil. Initial gas in place. Okay? That's what we define. And the ratio of those two numbers, okay, the ratio of those two numbers is the initial gas-oil ratio. It's just G over N. Or what we prefer to use is oil-gas ratio for condensates, which is just N over G. For example, with stock tank barrels per million standard cubic feet as an example unit. Okay? Now, what I've said here is that we're getting about, from the initial pressure down to the dew point, we're getting what that looks like, about 20% recovery of this G is being recovered down to the dew point, right? Okay? That's what we're saying. So, from PRI to the P dew point, we're saying that GP over G is 20%. Right? But what is NP? What is the producing oil in the same pressure range? The producing oil can be calculated directly from GP. How? Okay, by multiplying by this oil-gas ratio initial. Why? Because in this region here, the producing oil-gas ratio, which is what we actually have to produce, we have to multiply to get this. We actually have to do this, right? Okay? And I mean, to make it a general statement, we have to do this. Right? DG, basically this would be DGP instead of right. It's irritating. I don't know, there's something going on with the computer here, but this should be the integral, okay? Like that, right? From going at the reservoir pressure, initial, to the dew point. But if you say that in this region OGRP is equal to OGRI, right? Then that can just simply be written as OGRI times GP down to the dew point. Let's just call that star. And, okay. Let's see if this is working or not. I may have to, maybe because it's, I don't think this is working. Let's see here. How do you check if it's charging or not? Anybody know how to do that? Okay, so because this is okay for this condition when reservoir pressure is above equal to the dew point, then we get this, right? Okay, so then what is the recovery? What is the recovery factor of oil, which is NP over N, okay, in that region? Well, we can rewrite that as the GP times oil gas ratio initial, because that's the producing oil gas ratio at any time from the first day until you reach the reservoir pressure, right? But what is the initial oil in place? It's G times OGRI, right? So that means that it is the recovery factor of gas times 1, or it's just the same as the recovery factor of gas. Is it clear? Because the gas-oil ratio or oil-gas ratio is remaining constant from the initial pressure down to the dew point. So the curve will be in green here. And it'll look just like this. Okay? But then, as you go below the dew point, you get retrograde condensation dropping out of the gas, and the carrying capacity of the gas, carrying capacity of what? Of condensate drops. That's the little RS term, solution oil gas ratio, drops. And as a consequence, because the only recovery of oil we get in a gas condensate comes from what is being carried in the gas. That's important to remember. I don't care what your rail perms are. I don't care how rich your initial gas condensate is. At the end of the day, bottom line, whatever oil you recover is being carried in solution, in the gas, into the wellbore. Okay? Now I'm neglecting exactly what the flow phenomena going on around the wellbore, but essentially that's what's going on. So because of that, your amount of oil that's carried in solution in the gas, it's dropping. This is going to look like this. Okay? And the difference between the recovery factor of oil, which has, somewhere between 5 and 10 times the value per mole produced, it's got a lot more value than the gas, is very important, whether it drops off like that, or whether it drops off like this, or whether it drops off like this. Okay? It's very important how it looks, that oil recovery factor versus pressure.
Excuse me, will it be like this because then we have retrogrades at the low pressures?
No, you never pick up you won't pick up at low pressures a lot of this retrograde condensate. Now, the thermodynamics say that if you bring the reservoir to 1 bar, that all the K values of these heavy components are marching their way to very high values. Theoretically, you can vaporize the oil, right? From the K values getting higher and higher. But why don't you vaporize the oil? Why don't you get this big kick, what you're talking about here? Why doesn't it go like that? Because to get vaporization requires 2 things. Okay? Vaporization of heavy components requires 2 things. What does it need? No, heat is fixed here. The K values need to be high. Okay? The K values of the heavy component. C7. To vaporize C7, you want K value of C7 to be as high as possible. Okay? Because it's saying that component prefers to be more and more in the vapor phase. We go to low pressures, we get high K values. Okay? And it's inversely proportional to pressure, the K value. But that's not enough. That's the desire for that component to be in the gas. Okay? We all know we have lots of desires. We all want to drive a Ferrari to work, right? On a dry, nice, sunny day. Convertible, preferably. But why don't we? Because we don't have the money. Okay? So the capacity to vaporize the C7 is great at 1 bar and 280 degrees Fahrenheit. But you have to have something to vaporize it into. But by the time you reach 1 bar, how many moles of gas do you have? You don't have any moles of gas. I mean, there's a gas phase there, but there's not very many moles. So it saturates with C7. It's done saturated. Once it's saturated, okay, and then what's left is most of the C7 in the oil. Okay? That's why you don't revaporize. To revaporize at a low pressure, you have to inject a bunch of dry gas. Okay. There's a nice paper by Standing, one of the last papers he wrote, Standing and some people in the 1950s, I think, 60s maybe, on gas cycling at low pressures. Now this is what it'll look like. And what we want, this is the type curve of performance for depletion gas condensate. Okay? And actually the laboratory data from a constant volume depletion test gives you this information. Okay? It gives you the information because it gives you the composition and the amount of gas being removed as a function of pressure. So it's giving us all the information we need to create these. So in reality, what we actually have is we have data from the CVD test, and I'll just put that in black. CVD lab data. It's not, it starts at the dew point, but you can correct that to initial pressures. If you read chapter 6 of the monograph, it'll show you how to do that. And it'll basically look something like this. Of course, now I'm gonna go in red, and they're the same, and the red's going to be pretty much in line with what I'm saying our equation of state is. Something like that. It'll go down to about that pressure. Okay, and I'm going to say that the lines we have here, the lines are from our EOS model. And what I'm telling us is that if we use a PVT simulator model with CVD, or if we use a reservoir simulator model with the same EOS, we should get the same line. That's what we're going to try to do this morning. Okay? To get the same performance. So this is either a PVT model or a simulator. And that's the line. But what you may find is that the lab data, okay, the gas is going to be pretty much on, but the lab data might look like this. Okay, so that would be a discrepancy in your equation of state model ability to predict the carrying capacity of the condensate. Okay, so it's over predicting the ability of the condensate of the gas to keep condensate in solution. This equation of state model. That's what it's doing. Or the laboratory data is under predicting because of experimental error the amount of condensate in the gas. If there's a discrepancy there, it needs to be reconciled. So it can be data error, or it can be a bad equation of state, or both. But today's exercise is mainly to try to get consistency between the EOS model. The line should be the same if it's coming from a PVT simulator with a constant volume depletion experiment, or a reservoir simulator with the same equation of state and the same process and the same initial composition. And if you don't get that, then there's something wrong. There's something inconsistent. Okay? The other issue of reconciliation between the data and the EOS model, that's another problem. That's a PVT EOS modeling problem. That's a QC of the laboratory data problem. And those are also issues, but they're not really part of this course. Okay? But we may be able to touch on that briefly. But the point is that there's two lines here on the EOS. There's two lines, and those lines should basically fall on top of each other, which They won't if you don't get things right, if you don't get things consistent. Okay. And if you don't get the depletion performance right, okay, then when you're doing this course as EOR, then you start doing gas cycling and your depletion performance is wrong, then we're just playing games. Okay, we don't want to play games. So this is kind of a basic QC to make sure that you've got the equation of state, the surface process, all the consistency in the reservoir simulator model. And it's very easy to check to compare it with simulation results from a PVT program. Okay, so that's what we're going to try to do. But to do that, we have to have this consistency that I started with. We have to put in the numbers, the equation of state numbers right. We have to put in the compositions right. And we have to put in the viscosities, maybe not so important. The viscosity model should be the same, though that doesn't really matter too much. But the surface process is really often the problem in getting it right, wrong or right. So, okay. Okay. So that's the game plan here for what we're going to do. So we need an equation of state. We need to put that equation of state into the PVT simulator. Then we need to put the same equation of state into the reservoir simulator. And then we need to do the two simulations and start comparing numbers. Okay? Any questions about what we're going to do? All right. Then I'm going to start with an equation of state. Let's see here. See, the problem, let's see, the SPE3, I'm just going to go to that. My goodness, that's not what I know. Let's see, SPE3, phase mount files. I'm trying to find one that's consistent with what you've used in the course here. You've been using, does anybody have the data file you've been using here? Let me just pull this one of these up. Now these are the components. Okay. Now to do the comparison, this one has no volume translation. You've already been doing and talking about that. The original didn't have volume shift, right? And you found some volume shift factors?
Yeah, we had the both data files, so we worked on that.
Okay, so I'd prefer using it's with the volume shift. I'm not sure which values you have. You have them in the phase-com file. I'm just wondering if this is probably not the best data set. Let me see if I can find SP3. Then gas condensate here. This might be. Condensate SP3 US. Just there. Take the simulator data set. There we go. Okay, so we've got these. So we'll just take, I'll just take these. These should be pretty much the same numbers that what you have. I mean, it's not going to be. So I'm gonna. Let me see. This is. This is the EOR course. PG 8604. Is that right? Okay. All right. Let's see here. We can just look at the simulator data set. We've got 2 alternative surface processes set up. That's good. We'll probably use the C4 minus and C5 plus in what we do. We've got, I think this is a simple radial model. It's not the 9x9 4-layer. It's just a simple radial model. And then we got the EOS. Here we've got the 2 different ways of doing surface processing. And I'm going to create a little bit simpler model because if you introduce layers, then you start having not a single average pressure to do a comparison with. So I'm going to simplify this model. I'll put 1 layer. It's a radial model. We'll put 100 millidarcies in each one of these. Say the KZ is the same as, we'll just say this here. We've got 200 Fahrenheit, the US properties, initial pressure. Is that equal to the dew point? So let's give it some initial pressure higher than the dew point. Give it 5,000 initial pressure. So we'll have some of this undersaturated performance. We can use, the way it's set up now, we've got a surface separator that's got 46.5% of this component here going into the stock tank oil, and 100% of all these components going into the stock tank oil. It's called a split factor table instead of using an equation of state separator flash. So we'll use that. We'll have to use the same kind of factors in phase comp, and I'll show you how to do that in the simulator to create something we call a stock tank oil or oil, C5 plus. And then this perforation is just, we don't need K1 to K2 since it's only a single layer. The well's there. Producing at some rate for 10 years. We'll probably take that longer. Actually, we can, just to make sure everything's running, we'll just run it for a year just to see what happens. Is it clear? We got a radial model. We've got some kind of rel perm. I don't know if that shouldn't make any difference from what I'm telling you. If the only oil that produces practically is coming from the gas carrying, then the rel permeabilities don't really make any difference. Okay.
Last year we tried it and didn't affect actually. Last year
you tried that, yeah. So we can do that. And then we'll have to take and convert this into phase comp. That should be fast. Yeah, so I don't think there's anything special about this. We'll just run it. In fact, to begin with, we can just stop the simulator. We don't need to run it at all, just to see the initial gas place and initial oil in place, just the initial gas-oil ratio, because we want to get that to be the same in our PVT program, our simulator. Okay, so I'll just save this, and I'll try to run this data set. I have to go over and make sure I've got the right. I think that's right. Search initial. Okay, so we got initial GR of 7,228. We want to get that. We've got a warning here with oil viscosity is unusual, so we'll have to see what's going on there. We've got saturation pressure. Let's see, why is the... Oh, it's doing a bunch of... okay, let's just go up here and search for saturation. Maybe dew point. Okay. So we've got the 3480 dew point. We'll have to make sure our simulator, PVT simulator, gives the same. We want the same properties, densities, viscosities, and K values at the saturation pressure. So where's the saturation pressure K values? That's here. Okay. So we've got enough stuff coming from the simulator to make sure that when we go and bring this into the EUS simulator phase comp, we should get the same saturation pressure, the same K values, the same densities of gas and oil, same viscosities at the saturation pressure. And if we don't, then we've done something wrong in taking the EUS and composition from one model to another. Okay? So let's take that. And what I'm going to do is I'm going to take these properties here into the okay, so we'll do a US text file just to get it all in there. I'm going to bring these in to Excel to make this a little more easy to... We don't need the omega A and B's, but we do need these here. I'll put this up in the same there, and then we can bring those numbers in. I'll do it in Excel. Like that. You guys see this okay? Okay, and then we need some units. I'll just make this in the... This is Rankine, I think. We don't need these. This is a centric factor. In phase comp, this is called AF, volume shift, and ZC this. Those are the Okay. Enough, make sure we got enough digits. We look the rightmost is 0 and get rid of it. Rightmost is 0. Okay. We've got this is the characterization. We'll just call it, it's ARCO US, Pang Robinson US, something like that. Maybe just ARCO SB3 US. And the OS that we're using, I think it's Pang Robinson, is that right? And then we need the binary interaction parameters from that file down here. Into here. That doesn't look good. That was not good. Minus 0.02. It's actually the same one as here. That. Make everything look a little bit cleaner. How far do we need to go? We still got some non-zeros there. That. Okay. Yeah. And then we've got, what else do we need? Some kind of composition. Like here. This composition here probably has more digits than that's what we need. Point. There. How about format that? Like that. I'll show you a little different way of inputting compositions into face comp than we did yesterday. It's a little safer. You put the component names here like that. See, like so that we get okay. I'm going to say mix gas condensate. And we'll say it's in moles, just to clarify. Okay. So we've got a tank called GC. Is that right? And it's filled with these moles. And now we should be able to do some calculations like saturation pressure. That's the first one. So we do a mix feed. That says fill the PVT cell with a tank, the gas condensate. We'll use 1 mole of that. Okay, and then we'll set the temperature to, what was it, 200 Fahrenheit, I think. Don't need so many digits there. And then we'll do a saturation pressure calculation. Okay. And I'm going to save this before it crashes the whole system. Okay. So we can put in a title just to have one. SP3 ARCO EOS compare with sensor results. QC. Curtis. In class, February 2012. Okay. And then we got the characterization. And we have all the properties we need. We've got molecular weight, TCPC eccentric factor, volume shift, critical Z factor. For the viscosity, we've got the binary interaction parameters. We've got a composition. And then we'll do a saturation pressure calculation. And from that, it will give us some K values and things we'll compare directly with. This we don't need to keep. We'll compare directly with these K values. And then we need some properties, viscosities. That's not printed automatically. So we'll do a, we'll ask for that here. We'll do another experiment. CC experiment. Give it an ID. Get saturated phase properties. Pressure. Let's see. Stage. Okay, and then we can get. We want liquid density, gas density, liquid viscosity, and gas viscosity. Those are the main properties that we want. Stage 1. Let's see, we need pressure, we need units, and the units I think used by sensor output is what? That's pounds per cubic feet in centipoise, so we need pounds per cubic feet. Stage 1 and okay, so that's the experiment for okay. Are there any questions? What it'll do is it'll take from the saturation pressure, it'll fill in that pressure. It's kind of nice also to have we'll just print the temperature. It's not Fahrenheit. So it'll actually give, for this saturation pressure and temperature, it'll give us the liquid density, gas density, liquid viscosity, and gas viscosity. And then we'll use those to compare with the sensor. And the K values will be printed out when it does this. So we'll compare the dew point and the K values. This, if you ever do compositional reservoir simulation, if you ever get into this area as an engineer, what we're doing here has to be the first thing you do. Okay? Otherwise, it was a waste of your time to come to the university here and have me using my time. This is what I do. This is what all of my engineers do. This is what Keith Coates does. Any good engineer has to do this, to double check that from the one model, PVT SEM, to your Eclipse 300 or your CMG to PVT prop, inevitably through all the cuts and pastes and choices and radial bars that you have to click, something will be wrong. and you have to find what's wrong. And if we get it right first time, I'll be disappointed because it won't reflect even my having done this 100 times before. There's always some little mistake you don't think about. Okay? Now what we're doing it a little bit opposite. Usually you have a PVT sim program and you have an equation of state from that and you're going to a reservoir simulator. In this case we're going the opposite direction. It doesn't matter. Okay? The process is the same. And the tedious, boring, checking the numbers and doing all these things, that is why you became an engineer. It's not to point, click, and run the simulator and go get a cup of coffee. Okay? So let's do this. So I'll copy all this into a text file here. We'll call it US phase comp. Paste it in, save it, and run it. Hopefully we'll get something wrong. I don't have to do that. I can just double click on it. It'll run it. US out. Take that away. Okay, so then we go through. You guys are not real familiar with phase comps. We just kind of see what it says. It repeats the stuff that we put in. We put in PSI-A, Rankine, molecular weight, eccentric factor, all these things. It's got the Peng-Robinson equation of state. It's got binaries. Hopefully they're right. I mean, what I would do if I see any discrepancies in the calculated properties, I would start checking. But usually I'll check the numbers anyway, just to do a double check. So I'll sit there and take this output from phase comp, and then the output from sensor. I'll go to the properties table, start looking at those, looking at binaries, so we can go back and forth. I can do it with my eyes a little bit faster than you, just to double check some of these things. And if I don't see anything there, we've got the compositions. Those sum to 1 because you read in moles. Then it calculates internally mole fractions. So we didn't type an extra 0 or something in there. It does sum to 1, so that's a good sign. And then it's got saturation pressure in bar. I don't really want that, so I'm going to go change the units here. Somewhere here, I'll have to tell it to use units of. Well, actually, it comes in the next table. So. Let's see here. Down here in the CCE, it fills at 3481. Okay, 3481 at 200. So let's go look at the output from sensor. That's the output from sensor. We have to look for dew point. That's the wrong dew point. 3480.8. 3480.8. Again, unfortunately, it's too close. You get the wrong impression. We got 26.58 pounds per cubic feet. 26.58. We've got 19.13. 19.13. Viscosity 0.073. 0.072. 0.037. Well, okay. Unfortunately, everything worked this time. Don't think it's going to be that way. It's just because it is a lucky day. Okay. Now, gas oil ratio we don't have from the PVT simulator because you can't give in this PVT simulator. You can give those recovery factors as a process and have it create black oil tables with that process. But you can't have it do a separator experiment using recovery factors. So I would have to create a black oil table. There's a lot of stuff I'd have to do to get the right gas oil ratio. From the black oil table options of phase comp, it's a headache. You have to do it. It creates black oil tables, but not in a straightforward manner. And instead of me going in and trying to figure out how to get that in phase comp, I'm not going to do that. But I'm going to calculate the gas oil ratio myself for a given recovery factor set of tables. And the way I do that in phase comp is I can go up here and I can define, as we did in the sensor data set, a C5 plus component. Okay? So let's go back to here, and I'm going to find my process. We're going to define a process with component liquid recovery factors. Okay. And the way that basically works is that you say that you come in with a well stream, molar composition here with the number of well stream moles. Okay. You put it through this process, and you end up with moles of surface gas and moles of surface oil, which is defined as the moles of the well stream, moles of well stream composition, molar composition, times the recovery factor values here, from 0 to 1. Each component. So you say 100% of the heaviest component goes into the oil. Okay? And those factors are different for each component. And those factors are defined in the input data set of sensor, which we'll open up again here. Here. These number here. So it's 0 for all the components until C4 to C6. And of the C4 to C6 component, 46.5% is going to go into the surface oil. Okay? So we can define in our phase comp file, somewhere if we can find it here. Lump. We're just going to call it gas, or surface gas maybe. Maybe gas will be misunderstood. Surface gas. That will be all of CO2, nitrogen, C1, C2, C3, and 0.5. What was that number? Well, that's the amount that goes into the liquid. That's going to be lump surface oil. That's going to be C4, 0.465. Is that what it was? And then 1, 1, 1. Here, it's going to be 5, 3, 5. Is that right? Hopefully it'll print this out and it'll show us the numbers, so we'll make sure we've done this right. Okay, so let's just try that. Let's just rerun the phase comp file and see if it interprets that correctly. Files. So we'll go up the top and see. Okay, so you see it's got new lump fraction definition. It's all of the CO2, and then it's 53, so it gives the number there. And it's that much of that and all of those. So that looks right. Okay. So then what we can do is that we can create a PVT experiment to check the initial GOR. How should we do this? We need it to calculate the density and molecular weight of that surface oil for us. So we need to create a mixture with the surface oil. Let's see here. Okay. Okay. Well, if we get the let's see. So the question is how to get the gas-oil ratio from this. Okay, so the gas-oil ratio will be the moles of gas, right? Pound moles, let's say, times 379, right? That's standard cubic feet per pound mole. Divided by the moles of oil times the molecular weight of that oil divided by its density, right? And then we have, that's going to give it us in cubic feet, right? If you use pounds per cubic feet, pound moles and so forth. So if we take that mole, we've got to take that cubic feet and divide by 5.615 cubic feet per stock tank barrel. All right. So that's the same as 379 times 5.615 is 6,000, no. 16.
1600.
Can you give me a number? I think it's 21 something, but
Yeah, 21 straight line.
2140. Okay. Okay. That's the GR. Okay. Okay. So now let's conduct, we're going to conduct a gas condensate in the PVT simulator, a constant volume depletion experiment. Okay? And we're going to keep track of let's see here. Okay. So if the well stream we're interested in from the CVD test, okay, from the CVD test, you basically have two phases in the PVT cell You have some oil, and you have some gas, and then you've just removed some of that same gas, right? That's what's been removed. And we know basically how many moles of gas have been removed, right? And we know and we can ask it for the composition of that gas in terms of the Sg lump component and the SO lump component. We can ask for the mole fraction of those two, and it'll give it to us. But if we're interested in the GOR of this removed gas, right, then this term here, okay, for CVD gas, Ng is going to be 2140. Ng is going to be just Yg, okay? Because the moles is the moles Ng times Yg, right? Divided by the moles of oil is Ng times YO. But of course that how many moles you remove doesn't matter to the ratio. Okay? Yeah. So all we need to have printed from our experiment is really the mole fraction of either the surface gas or the surface oil, because that you can just rewrite as 2140 1 minus YO over YO, right?
On the equation 2140 Ng by NO, did you miss molecular weight divided by density?
Okay, yeah, we need this term here, which is going to be rho O to MO.
Yeah.
Right. Okay. All right. So we need to print the molecular weight and density of that component. All right. Okay, so let's create a PVT experiment. We can do that. Have we changed this data set here at all? I think that's all in the Excel file still. Okay, so just continue with this. We'll make a new experiment. Okay. Okay. Let's see here. We want to. What we want to do here is have our reference pressure and temperature, the initial in the reservoir. Temperature is 200 Fahrenheit. Okay. And in fact, we can say that the PVT cell contains as much material as the reservoir model, if we want to. I mean, it doesn't really matter, but if we want to look at recoveries, so we could look at the output of here just for the fun of it. We can initial, and we can say that the initial hydrocarbon volume is that. Okay. 16497 thousand barrels. 14, so this is basis. 1647 barrels. Okay. At that condition of 5,200, right? 16497, 16497. That. Okay, and then we'll do, at each stage, we'll have a pressure. And let's see here. So what do we want to have? We want to have how much gas was taken out, moles of gas removed, and we can take that in standard cubic feet. Okay, now that's going to be that's going to basically be this number here. Okay. And of that, what's removed, we want to know the composition of what becomes surface gas and surface oil, right? But that's simply the mole fraction of surface gas and mole fraction of surface oil, Sg and So, that we defined. Okay? It'll take the actual full component slate and it'll use those recovery factors and tell us what's the mole fraction of Sg and the mole fraction of So. But in reality, we only need one mole fraction, right? We only need the oil mole fraction. So I'm just gonna print the Y, that's the mole fraction of that, of Sg, and it'll be in fraction instead of percent by default, so I'm not going to put percent. We'll be using that to multiply. Except that should be SO. I'm going to use SO. The mole fraction of the surface oil. What else do we need? We need the molecular weight of the surface oil, right? We need the molecular weight of the surface oil. It'll also give that. It'll actually calculate using those recovery factors. Now the problem is it's not going to give us the, I can't ask for the density or specific gravity. That unfortunately doesn't come automatically. So we're going to have to do something else there. Okay. Exactly how to get that I'm not quite sure, but we're going to have to take that composition and save the, we want to save the take the whole gas composition, and then if we extract only the C5 plus part, that's about the only way to get those densities. So I think or let's see here. What was the saturation pressure? 34, 3480? Okay. Okay. So here we'll have how much gas is being removed each time. Here we'll have the mole fraction becomes surface oil. We have the molecular weight, surface oil. And then the density. Let's see here. Let's see if we can try to extract that. The molecular weight, what it's going to do of this, it's going to take this is a component. It's going to, and we're of the gas. It's of the gas phase. So this is of the gas phase. It's going to take in the simulator, in the PVT simulator, it's going to take the gas composition, calculate the total mass. It'll take the gas composition, times the recovery factor of that particular component. That's what's going into the surface oil phase, times the molecular weight of the component, divided by, this is the total mass of that surface oil component, times the moles, which is this. Okay? That'll be the molecular weight. The density of that surface oil that evolves from the removed gas is approximately, if you use ideal volume mixing, then it would be, then we could use the specific gravities of each of these components. And let's see here. That would be the same as this here. That would be the mass. That would be the same. Here. And then it would be divided by the ideal volumes. Okay, which is these are the masses divided by these liquid densities for each of the components. Okay. This represents the sum of the ideal liquid volumes. This is the sum of the liquid, basically of the masses that become surface oil, right? This is the fraction here of what's removed as gas that turns into surface oil on a molar basis. And multiply the molecular weight, then you get the total mass that becomes surface oil from reservoir gas. Now what we're really wanting to do is that we're wanting to convert to a volume here, right? That's what we really want. So what we'd really like to know is what is the surface volume here per mole of that. That's what we'd really like to know. But that's equal to this over this, right? That's volume, surface volume per mole. But what is that? Well, if we take that divided by that, then you see this term cancels, right? So that if we call this, whatever you want to call it, this term here, it's usually called molar volume. This term is usually called molar volume of surface oil coming from the gas. That would be equal to that. And that's equal to this term here, divided by that term there. Right? Yeah, I don't really see any way to get this clean way. Let's see here. Um, Yeah, I think the only way to do it, because in essence we need to pass the removed gas well stream because in the simulation what it's taking the removed stream and putting it through this process, and we really need to do that with the experiment here to get the amount of gas and oil. But and we can get the moles that turns to surface gas and surface oil, but getting the volume of the surface oil, it's not trivial, because you have to basically process out from the removed gas the composition of this surface oil, and then take it to the equation of state to get its volume. That's what really has to be done to do it right. And so we can do that because what we do is we take the equilibrium vapor here, and we can store that removed equilibrium vapor, put it in a tank. We'll call it gas 5000. Oops. Gas 5. We'll put a tank there. It'll be another tank, gas 4500. Of course, these are all going to be the same down to the dew point. These will be tanks, so we don't really need those. But when we get down to the saturation pressure, which was 3480 approximately, or 34. 3480.8. And then for each one of these, we have to do a we have to basically extract out only the surface oil part by the split factors and take the resulting feed oil to get its density. That's about the only way to do this manually. So it's a real pain. Well, I can do it for one of them and then repeat it. So that's going to be, we're going to mix, and actually this, all of these are going to be the same here, so we can just start there, because all of these are going to be the same above here, same composition, right? So we can just take, and we can say multiply the components CO2, C7 plus 3. And G 3480 by no, let's see. All we have to do is we have to multiply. We're going to get rid of all the light components, so that's going to be down to C. Get rid of the light components to C3. So that gets rid of all of those components. So now the tank, this tank G3480, has gotten rid of all of these light components. But we also have to get rid of this where's the lump command here? Was that in the file? Okay, these I didn't. Okay. Put those in there. So this, we have to, we've gotten rid of those, and we need to get rid of this much of the next component, 53.5. And that component's C4.6. 535, is that right? 535, C4, C6. Okay, so now what's left in this tank here is just the C. Yeah.
So I think the first one should be multiplied by 1, not by 0. Right?
Well, what we're trying to get is we're trying to get this to contain only the surface oil part. So we're eliminating the light stuff by multiplying it away. Okay? So what we're left with is 46.5% of the C46 component and all of what is C7 plus. So we're kind of removing the light stuff here. Yeah. Well, but it's still left there. We're not doing anything with it. It just keeps what's left there. So now what we have left in this tank is just 46.5% of this component and all of the C7 and heavier. Okay? So now what we can do is we can just normalize that to 1, if we want to, and go off and calculate its density. Okay? So now if we just do mix G3480, and now it'll create 1 mole of that. It'll just normalize it. And then we can set up a temperature, 60 Fahrenheit, pressure, 1 atmosphere, and then just do a flash, that will give us its density from the equation of state of that mixture. And then we're going to have to hand pick that density to use together with the molecular weight here. So it's kind of cumbersome, but this is basically stripping out the gas components. What you're left with, you do a flash at standard conditions. So this is going to give us the density of that oil. That'll be the same process that actually Sensor is doing in the simulator. It basically strips out the gas components, calculates times 379 to get the standard cubic feet, strips out the oil component, sends it to the equation of state, calculates the oil volume. That's effectively what we're going to do here. Now, that's just for the first one. This has to be repeated for each of these. Okay? Pain. So let's just try it the first time for the first one and see how that works. Okay. And then we'll have to put that together with the molecular weight here. We've got the gas removed, which is the standard cubic feet. That we can also actually, I'm just going to keep this in moles, I think. Pound. Not sure how it's written. Pound moles. Maybe. Let's see. Okay, let's try that. See what happens. Like something. Gas removed. CVD, basis, stage, pressure, gas removed. Gas removed. Maybe moles removed. Yeah. Gas moles. Okay. Yeah. Gas moles removed. Okay. Try that. Gas moles removed. Maybe it's just moles removed. Yes. Moles removed. CO2. Okay, moles. Okay. Okay, multiply. I think it's multiply moles. Okay. All right, so we've got still got our 3480.8. Okay, we've got, it's storing these tanks. This is the moles removed. This is the surface oil lump component and the gas. So if we multiply moles removed by that fraction, then we should get the moles of surface gas removed. I've got the molecular weight. You can see that's not changing very much of the surface oil. Then it goes in and it multiplies this and the 3480 by 0, and we end up with the composition here, except we didn't get rid of the CO2. This is strange. Equilibrium vapor. That didn't work. So it's not doing the. Maybe we should just see what we have in the way of when we get out of this. When we leave, let's just see what we have as a gas composition there when we finish. It should be storing this gas from here. Yeah, see, it's not filling that tank, right? 3480. Equilibrium gas. Strange. Why is it pure CO2? Oh. Okay. Okay. This is. It has to look like that. It's making a new tank from the old tank. Before it was just making a new tank full of 1 mole of first component. So that's there we go. There we go. Now we got our gas. Get rid of the CO2. Down through there, we got a little bit of the C4, C6 plus left. We do a flash calculation. Should be a liquid. That results. Now we've got a little bit of a problem that liquid is splitting into 2 phases. And that's not good, because the stock tank liquid that it's getting, surface oil, is splitting into 2 phases. And now in the simulator, when it takes that oil, it's not going to do any flash calculation with it. because you're saying you don't want to use the separator flash. You're going to use the component split. So it's going to take that overall composition here, except, okay, well, maybe the problem is that it's got the wrong stuff here. It's not taking this. Okay. Okay, so we were using the wrong material here. Okay, I see. This should be mix feed. Yeah, that's to fill the PVT cell with that. Okay. That's the problem. You see, it was not filling, it was not doing the flash with the stock tank oil. It was using the whatever was coming from somewhere else. So we have to change this here to feed like that. There we go. Okay. Okay. And it's doing still seems to get two phases. It's not good. Still. Okay. Do you all see the problem? What's happening is that it's splitting out the components that you say you want to be surface oil. But if you try to put that into the equation of state, it'll split into two phases. It won't be a surface oil. Okay? Now some reservoir simulators will actually try to do a flash of that, and others will just say, whatever you tell me is there, I'll consider it an oil. And they'll calculate kind of a pseudo oil volume. So the programs are going to give different results. And that's often a problem in using these split factors, or recovery factors, for a surface process, is that you don't get a kind of a thermodynamically consistent result. So what we're going to do now to avoid that is that I'm not going to let any of the C4, C6 go into the stock tank oil. It's making it too volatile. Okay? That's what I'm going to do is change that. So in the simulator, in the reservoir simulator, I'm going to change the recovery factors, wherever that input data set is. Okay, I'm just going to make this 0. So it's going to be a stock tank oil is going to be C7 plus. Okay, it's not a very efficient process, but it's for the sake of what we're doing, we're going to. So we're going to change this. We're going to have C4 minus, and it's actually going to be C7 plus, and C6 minus. Okay. Now when we rerun this simulator, is this initial fluid in place going to change?
No.
Not the reservoir barrels, but it's definitely going to change this 7228, right? So let's just rerun the simulator and see what we get. Yeah, so you got 11,000. You got a lot more gas and less oil, but this number shouldn't have changed, which it didn't. Okay. Okay, so now we have to go to the go into here, change our lump. I just change surface gas is we'll just take C46 here, and we'll just C7 plus 1, C7 plus 2, C7 plus 3. So that'll be what we define as surface oil and surface gas. Okay, and then we'll come down here. So now what we get in the way of surface oil will be different. Its molecular weight will be different. It'll be higher. And we'll get a different result down here. So let's bring all that in. That, place it, rerun this, US. Hopefully it's going to be single phase, what we end up with. So now you see it, this is still not right. Oh, okay, that's because we didn't change these. I can get rid of this line, right? Okay, now we got only the C7 plus coming here, and now we have its single phase, and it's actually doing what's called a negative flash. It's allowing it to do a negative flash. So I'm not going to let it do that. I'm going to force it to not allow negative flash. So what we'll do is that we'll write up here stability. I don't remember the on. I'm not sure what I have to go check the manual of this. Stability. Let's see here. Initialize stability. Here it is. Stability on. So that means it'll never accept a negative flash. So I think stability on is the keyword. Stability on. All right, again. And you see now when it does the flash, it forces it to be a physical solution, which is and now you see that what we come in with is considered liquid, and this molecular weight should be the same that's up above, 133,663. It's 133,66. But the density we now get down here, and that's 0.781 grams per cc. Okay, and then whether that changes much with the as it depletes this gas condensate, whether that changes much as you deplete, the only way to find that out is to take and redo this same thing here for a number of these other mixtures. Okay, so I can do a few of them. Do them all if we weren't getting tired. So I'll just go in and do some of them. We'll do 3,000, 2,000, and 1,000 just to get a feel for it. Okay, so let's see, we have to do it. It's just what's been selected. Do you know how this works? Whether it only take what's selected or not? Should we take a chance? That was nice. It worked. Okay, 1500, 2000, 25, 3. Okay, so we'll see whether that density changes much or not for these different ones. Okay. Okay, so we got 781, 776, 773, 77, 767. So it's not changing much, but at least we now know the magnitude of that change. Okay, so now the question is, if we take for this first mixture and see the CVD test here, can we get the same kind of cumulative gas produced at the dew point? I mean, first we have to get the same GOR. We have to make sure that we get the same GOR from the two. So the GOR from the simulator is 11,014, right? So let's see here, where's the pen? We get this to work, then we'll take a break. Okay, so the GOR from phase comp was this 2140, right? And it was times the basically the 1 minus mole fraction of oil, and then times that ratio of density to molecular weight in pounds per cubic feet. Okay, so 1 minus, and then we have to go to the okay, 1 minus, this is the mole fraction, right? Becomes surface oil from the reservoir gas. So 6.6% becomes surface oil. 0.659. Divided by 0.0659. We need the density. Multiply that by the density of the oil and divide by 133.66. And the density was down here, 781. But we need it in pounds per cubic feet, 62.4 approximately. So what do we get? Anybody have a calculator or not? Okay, we got 11,057 standard cubic feet per stock tank barrel. And that's versus 11,000 and what was it? From 11,014.
If you give the exact number, then
Well, this number here isn't quite exact.
that was 2128.
Two.
2128. 2128. The multiplying factor.
Oh, should be 2128. Okay, yeah, that's a number that's more familiar. 2140 is 2128. And then what do you get here? What do you get here with 2128?
It's also with the 1998.
1099.
Yeah.
We say 11,000. Is that close enough? So, I mean, we're close enough for the 62. Should be 6242, I think. There's a few little things like that, but okay. So we're basically, we've got the same number for that. Okay. So the gas in place and the oil in place should be the same from the simulator and the PVT. Now we've got to see whether the recovery factors from the constant volume depletion is. Let's see here. Save this. Okay. So now we've got the recovery that we have to calculate. We can do that from these results. I'm going to close all of these windows here, and then what we'll do, we'll take a short break. But if so, I think that our initial gas in place, G, and the initial oil in place, N, these are the same between the two because we start with the same reservoir volume. We haven't completely checked that, but we've got the same initial GOR. Okay, that's basically from that. Now the question, as it depletes from 5,000 down, are we going to get the same number of moles produced and the split, the compositions and so forth? How are they going to compare? Well, in the simulator, do you see any difference between the reservoir simulator and the PVT experiment? What are some of the differences you see or that you've noticed? Okay, what's one difference? The PVT simulator has no water in it. Okay, now does that really matter? In the simulator, there's no thermodynamics between the water and the hydrocarbons, right? But in the PVT cell, in the simulator, the constant volume depletion, what does constant volume mean? The hydrocarbon pore volume remains unchanged. But what about in the reservoir simulator? Huh? Yeah. It's got water. As the pressure drops, what's going to happen to the water? Expands. Okay. What about the pore volume? So let's look at the data set for the simulator. Okay, and this number here is the compressibility of the water. If I want my system to be like my PVT simulator, then you have to make that 0. Okay? What else do we have to make 0? Well, the rock compressibility has to be 0, right? Now the pore volume, the hydrocarbon pore volume, should remain constant in the simulator. Okay. If you leave those water in there, then what is going to happen to this behavior here? What will happen to the line, which is the model, with water, without water? It'll shift upwards because you're getting pressure support. Okay? Okay? And if I left it in there, which I usually would do if I hadn't wasted so much time getting where we're at now, I would actually let us be confused, because the simulator is going to give more recovery at a given pressure than is the PVT simulator. Okay? And you're going to think, well, it's not really simulating the same process. We're doing 500 PSI pressure drops. It's not, there's no relative permeability. Okay. But at least now we've eliminated the pore volume difference. Okay? And so what I'm going to do now is I'm going to get rid of this end. I'm going to run it for 10 years. See how far the pressure depletes. I don't know. I just want to see how far it depletes to see. Okay, average pressure is down. Okay, it depletes far enough down. So we've got 1,000 pounds here. We got 2,000. Here's 2,000 pounds, pretty close. So we've got a recovery factor at 2,000 pounds of 47% gas, 32.5% oil. Okay. Can somebody write those numbers down? So we've got 32.5, 47. So 32.5, 47. Oh, at 2011, that's recovery factor oil, recovery factor gas, and average pressure. Okay. Let's increase the permeability to 1,000 to make less pressure drop in the reservoir. It'll be more and more like a uniform. Just curiosity. Okay, we got to find 2,000 on the pressure. So we got a little bit plus minus 2011. Okay, 33.1, 46.8. That was at 2021. So this is K100, K1000. Kind of gives you the magnitude of change. I mean, making it more and more. This is a little bit more than line thickness on the oil, but not too much. Depends how thick the line is. Okay. Okay. Then what we need to do is take the EOS out results and process those into recovery factor. Okay, we've got a little bit on this density of stock tank oil changing, but not too much. I think we're going to ignore that and just take these results into an Excel spreadsheet and do cumulative moles removed. We're going to separate that into surface gas and surface oil. We're going to add up the oils and up the gases, and when we get down to 2,000 pounds, we're going to find out how much of the original oil, surface oil and gas that we have produced. And those numbers will compare with these numbers here. Okay? Okay. Okay, we've got pressure, PSIA. Let's see this. This we don't need. This is moles produced, right? This is the mole fraction. We'll just call it the YSO. This is molecular weight, SO. And then we're going to go for a density, pounds per cubic feet. That's varying a little bit, but this is pounds per pound mole. Okay. And the density we're going to use is what? We had 7, 8, a little bit less than 7, 8, 7, 7, 7, 7, 5 on average. 7, yeah. We can study the sensitivity of that up there. I'll put that in red because that's something I can change if I like. And we'll just fix 62.4 times that. Okay. So then we need to know what's the initial oil in place and the initial gas in place. And to get that, we need here. We got this many barrels, but we need to know how many moles there are, right? And right now it only tells us the moles removed. So what we're going to do is ask for this also to give just the moles. I think it's just written like that. Okay. So we've got this many moles. 6.5061, 10 to the 7th. 6.5061, 10 to the 7th pound moles. Should we check that against what it has in sensor? I think probably is worth doing. Does it give moles somewhere? Okay, initial moles in place. Take all those together. Should that be right? Six, 4, 9. Six, 5, 0, 6, 1. Close. Not completely happy with it, but six, 4, 9. And this was okay, 0.2%, that we can accept. All right. Okay, so then 65061, 10 to the 7th. Initial moles. Okay, and we've got then we need the gas in place and the oil in place. Okay, so that's equal to the moles times this, what, 1 minus this first fraction? That's how much turns into surface oil, times 379. Right? To 23 BCF gas. (23 BCF of gas). Okay. And then we need to get the number of moles of the oil here. And that'll be the number of moles times the mole fraction times the molecular weight divided by the density. And that's cubic feet. So divided by 5.6146, so 2.11 million barrels. Pretty close. A fraction of a percent. Okay. Now the difference is is this one here. So if we want it to be 2008, remember that should have been 0.78 something. It's getting closer. So it's a trade-off. It's having that magnitude of an effect. The densities here were .7811. We should be getting, the further we take this, the closer we get to the, so it's getting pretty close. Okay? So, now we have to calculate this oil produced, gas produced, MP, and the recovery factor of gas, recovery factor of oil. Like that. And to do that, we have to take the difference in cum here times so a little bit of the problem is that we've got this discretization. You know, basically we've got changes. And so what I'm going to do is I'm going to create an extra column here where I actually calculate an average mole fraction over the period. Okay? Insert. So this is going to be YSO average. Okay? And that'll be average. See, the way this is, just to sketch it, basically the CVD, the continuous change in basically YSO is like that from the simulator if you looked at the time steps there. And what this is going to do is that when it reaches the dew point, it's going to let's say it reached the dew point on a time step there, then it should be giving what we're taking is the equilibrium composition at this point here, and assuming that it's, I think it's going to be on the underside of this. I'm pretty sure it doesn't look like that, because these compositions we get from the CVD are the equilibrium compositions at the end of the time step. Okay, so I think it's something like that. So if we want to bring this kind of average up, we take the previous. See, how would we do that? Actually, this should be going like that. So how would we calculate that to be correct? We would take what we actually have plus the previous one and use that, I think. So I think we'll try that. Average of this to that. Okay. And then we'll use the moles produced in that increment times the average, except it's 1 minus this times 379, right? Okay. Okay, and then we've got the same thing. Moles times the mole fraction that becomes surface oil times molecular weight divided by density divided by 5.6146, something like that. These are actually D, PP, D, and P, like that. All right. And we take the previous plus the incremental. And then we take that and we use this. And we got 47% recovery of gas and 33% recovery of oil. Was that 47? I said 44. I said 47 and I wrote 40. That means we're getting tired at 2000. Okay. Okay. And that's the way it should be. Now, I don't know how many weeks last year you used to try to get this
So much.
process. Weeks at least. Individual groups all suffering through the same different kind of things. Now, all I can say is that we stumbled through it in 2.5 hours, and I realized that we had no breaks. Luckily, nobody had to go to the bathroom, I hope. At least I didn't. I'm the worst. And we basically went through several processes. We did the EOS consistency check. We did the surface processing. It's not easy. We ran into several problems. The two-phase split would have caused problems in consistency because sensor would not have taken this C4 plus oil, C5 plus oil. It would have assumed it was a single phase, whereas we would have had a problem getting from phase comp what that single phase property density was. A number of things like that would have been differences, so we had to kind of create something that was apple to apple, red apple to red apple comparison. This little thing on the integration helps because the discrete steps of 500 psi are clearly much bigger than in the simulator. There's a number of things like that. But at the end of the day, this plot reflects what I call a type curve of depletion recovery performance for gas condensate. It's independent of rel perm. If you don't believe me, you can take the data sets that I give you. You can change the rel perms. You can make your own sensitivities. You see, when he walks in the door, the lights go out. This is a spooky guy. Okay. And it's a type curve. This curve reflects pure PVT. And the great majority of recovery performance, depletion recovery performance for a gas condensate is pure PVT. It is simply the carrying capacity of the gas to hold condensate in place. The equation of state may not predict it accurately. You probably don't know that's the case, because when you do tuning of the equation of state, you fit liquid dropout, not the carrying capacity of the gas, which is composition. But the simulator giving you the same performance, the reservoir simulator and the PVT simulator, they should have the same kind of performance. And the way to make sure of that is to go through this kind of process. Now we can put back in compressibility of water, compressibility of rock, aquifer, layered performance, and everything else. But what you should know is that any cell in the model experiencing depletion is being controlled by the PVT describing that cell. And the only way to make sure that that PVT is describing it properly is to go through this kind of an exercise. Okay? It's also a nice exercise because you can study the effect of water, of rel perm, and so forth for your gas condensate. And anything that makes it deviate from these, call them the type curve, the PVT type curve of performance, recovery factor of gas and oil, making it better, making it worse. Basically, you have this reference behavior that goes back to the PVT data. If you have high quality PVT data, the symbols, you want to make sure that your lines go through those symbols as closely as possible. Okay? That's your PVT quality fit. I mean, it's the quality check on how well your equation of state describes the PVT data, which next week he's going to have to defend because he's been developing an equation of state for a gas condensate field in Colombia. The Colombians don't mess around. You screw up, the mafia. So he okay. So this plot, you don't get it in the PVT report. You have to create it yourself, and you can make the comparison and see. Okay. Well, if I lost anybody, then you have the unfortunate pleasure of being able to re-listen to the video when I hit this red button here.